Very good morning, friends. Myself, Professor M.H. Annaya, and in today's video, we are going to work out a problem on a steel plate having a hole drilled at its center and subjected to a bending moment. Something like you have got a steel plate, it has got some thickness and width, and there is a hole drilled at its center and it is subjected to a bending moment of a given value, and we are going to find out what is the maximum stress induced in the member, taking stress concentration into account. Friends, first of all, let us see the question given. So I will just write down the top and front views of the plate given with a hole drilled in it. So this is the front view showing the cross section, and this is the hole drilled at the center, and this has got a thickness h which is equal to 5 mm. Sorry, thickness is 10 mm. Thickness is 10 millimeter, and you have this top view of this like this. The width of this can be seen here. The width of the plate, which you call it as B, is given to be 50 mm, and the thickness is 10 mm. The whole diameter, which is drilled here, is given to be 5 millimeter dia. So this is 5 mm, or you can say 5 mm diameter, 5 pi or 5 pi. And friend, it is subjected to a bending moment like this. I'll call this as MB, which is given to be equal to 800 Newton millimeter. So when it is subjected to a bending moment like this, is asking us what is the maximum stress induced in the member, taking stress concentration into account. Friends, we will start this problem by writing the formula for the stress concentration factor. So in general, for bending, the stress concentration factor, SCF, is stress concentration factor, that is designated by K sigma, similar to our axial loads. So this is given by the ratio of maximum bending moment, sigma B max to sigma B nominal. So friends, to find out the sigma B maximum asked in the question, it's a product of K sigma into sigma B nominal. So this is the equation. So to get the value of sigma B max, we should know what is K sigma and what is sigma B nominal. Friends, here for the given plate, if you refer to the data handbook, a graph is given along with the sketch of this, same sketch, and the graph runs like this. You have on the x-axis the ratio of d by root plotted along the x-axis, and along the y-axis you have got what is called K sigma plotted along the y-axis. And friends, there are a lot of curves available here. There are a number of curves for various values of d by h. Number of curves are there. So our aim is to find out K sigma. What do? We will find out d by w or d by b, say b is the width of the plate, d by w and d by h. Let us find out the ratio as per the sketch given here, and let us see how to calculate K sigma. Now friends, for the given plate, d by b, d is the diameter of the hole, that is 5 millimeter, and b is the width of the plate, that is 50 mm, that is 1/10, that is 0.1. And similarly, we need to know what is d by h. So d by h is the ratio of diameter to the plate thickness. Diameter is 5 mm, thickness of the plate is 10 mm, that is 0.5. So we have got two values. One is d by v value, other is d by h value. Friends, corresponding to this d by v, that is 0.1 we have got here. From that d by v equal to 0.1, write a vertical line till it cuts or intersects the curve with d by h value equal to how much? 0.5. There will be so many curves, you have to go only up to that particular curve which has this ratio d by h is equal to 0.5, and write a horizontal line from there, from the point of intersection of the vertical and that graph, and you will get the value of k sigma here. Friends, this k sigma works out to a value of 2.3 approximately. This is 2.3. So we have got k sigma. And remember friends, in the same graph, they will also give you the expression for the nominal stress also. So we have got the value of k sigma, and by finding out the value of sigma b nominal, that is the equation of that sigma b nominal is given in the same graph at the corner of the graph, and you will say sigma b nominal is equal to 6 mb divided by b minus d into h square, b minus d multiplied by h square. So this is given in the graph machine design handbook. The graph itself they have given this. Where you are referring to this graph, you will get this equation. It is 6 times mb. 6 times mb is bending moment. It is given to be equal to 800 Newton millimeter. So it is directly 800 divided by b minus d. B is the width, that is 50, minus the diameter of the hole drilled is 5 mm, minus 5, multiplied by square of the thickness. Thickness is 10 mm, so 10 mm square. Friends, if you simplify this, you will get this value of nominal stress as 1.066 Newton per mm square. So, friends, we have the value of k sigma, we have the values of the nominal stress, and hence we will be able to find out what is the maximum stress induced in the member. Therefore, sigma b maximum, that is the maximum stress induced in the member, is k times sigma, k sigma multiplied by sigma b nominal. Friends, we have this k sigma from the graph 2.3, and sigma nominal is 1.066. So that works out to finally 2.4618. 2.4618 Newton per mm square. Friends, this is one of the important questions on a flat plate subjected to a bending moment. Friends, I hope the presentation was interesting and useful. And if you like this video, do share with all your friends without fail. Have a nice day.